So hello everyone, welcome you all at Loki's Sir Unlimited Study Zone. We're starting the topic here, electromagnetic induction. Okay, so both the words are here, electro as well as magnetic. Okay, simultaneously two words are here. One is electro, second one is magnetic, and something is called induction. So first thing, do you know what is induction? There are two type of um, you can say communication of effect or two type of connection between any two bodies. First, that is called conduction. Okay, first is called conduction. What does it mean, conduction? When you touch any body, like you have a body positively charged, okay, beta, and you connected this body with some another uncharged body, with another uncharged body, okay, directly contact some through some wire. So positively charged also is get spreaded over this body, right? So this thing is called conduction. So in conduction, there is a direct contact between the two bodies. This thing is called what? Conduction. Okay, conduction. Another is called induction. Induction means conduction. Def- This is conduction. When there is a direct contact between the two bodies, is called conduction. Okay. And now we are talking about induction. So what is induction? Without any physical contact. When there is a term induction, this means there is no any physical contact. So without any physical contact, right? Physical contact. Yes. In electricity, we have also seen the induction method of developing the charges. How? You see, this is the negatively charged body, right? This is a negatively charged body. And in nearby, you have kept a positively charged body, sorry, a uncharged body. So due to this negative charge, positive charge cloud will be generated here. Okay, the electron displacement will take place. So positive charge will be moved towards the left and the negative charge move towards the right. Clear? Now you ground, if you ground these charges, so as the positive charges are hold tightly with the attraction of these negative charges, but negatively charged are grounded. So after grounding, you have a situation like this. This is negative charge spread all over the body. Okay, and here as the negative charges are grounded, so only positive charge or positive charges are left. Okay, on the body. Yes, here it is positive. All the positive charges, nothing negative. Right? So this is what? This is induction. Yes, induction charging. This is called induction charging. Understood? Yeah. So you have seen that there is no physical contact. Okay. In the same way, the name of this chapter is also electromagnetic induction. Okay. The name of the chapter is electromagnetic induction. Means there is also some type of induction will take place. Okay, in coming classes or in coming time. So thus induction process will take place. Let us start with the definition of electromagnetic induction. So quite simple. It is definition of electromagnetic induction. I told you that in the earlier 16th century, Michael Faraday flows a current, okay, through a current conducting through a straight wire, and he convey the magnetic field surrounding that wire in the form of concentric circle, right? So this is the discovery of magnetic field with the help of a current carrying conductor. So this is said to be the discovery of, yeah, discovery of magnetic field with the help of current carrying conductor. Yes. So from current to magnetic field. Yes, this experiment is performed by Hans Christian Ørsted. Okay, yes, at the beginning of 17th century. But at the end of 17th century, yes, at the end of 17th century, Michael Faraday performed the production of current with the help of magnetic field. With the help of magnetic field. Okay, so this thing is called, this phenomenon is called electromagnetic induction. Let us read the phenomenon of generating current and EMF. Obviously, when there will be EMF, then only current will be flow, because without of EMF, as plus and minus polarities are there and circuit is closed, then only current can flow, right? So first EMF will produce, then after induced current will be flow. Okay, first EMF will produce. The EMF produced during electromagnetic induction is called induced EMF. Okay, the EMF produced is called induced EMF. Yes, EMF produced during EMI. During EMI, electromagnetic induction is a big name, so I will abbreviate this one as EMI. So the EMF produced during EMI is called induced EMF. Yes, it is what? Induced EMF. Okay. And whenever the circuit is closed, whenever only the circuit is closed. So as a result of this EMF, as a result of this EMF in the closed circuit, current will flow. Surely, yes or no? Current will flow. And this current is called induced current, right? So this is said to be induced current. So two things are there, induced EMF and induced current. So first there is a production of induced EMF. After then if the circuit will close, then there will be a flow of induced current. Okay. So the phenomenon of generating current. Okay. The phenomenon of generating for current. But first it should be, there is a generation of EMF. Okay. That is called induced EMF by changing magnetic field. What I said, there is a production of electric current with the help of magnetic field. Yes, because the chapter name is electromagnetic induction, and in this induction there is the production of electric current with the help of magnetic field, but not by constant magnetic field, by changing magnetic field. This thing you have to remember. Constant magnetic field cannot produce electric current, only a changing magnetic field. Yes, so if there is a delta B, means changing magnetic field, it will induce some current in a circuit. Clear? So delta B means changing magnetic field. Yes, changing magnetic field. Clear, beta? Okay. So the phenomenon of generating current by changing magnetic field is called electromagnetic induction. Its full name is EMI, right? Later on, we will see in what way we can change the magnetic field, and we can produce, we can induce the alternating EMF or the electromotive force. Okay. Second thing, second topic, induce EMF and induce current. The EMF so developed is called induced EMF. As I said, during this process of induction, as induction is takes place, there is no type of conduction, not any type of conduction. So the voltage produced, or you can say here the EMF produced, because the maximum value of voltage is called EMF, right? Yes. So the voltage developed or the EMF developed, okay, any across any two terminal of the circuit is called induced EMF, right? If the conductor is in the form of a closed circuit, then the current will flow in the circuit. This is called induced current, right? The phenomenon of EMI is the basis of working of power generator. Yeah, on the same process, we generate the power in the power stations, and the dynamos and transformers all are, the working principle is electromagnetic induction. Okay. So all the great devices, the phenomenon of EMI is the basis. So all the devices working on the basis of the same process is electromagnetic induction. And the name of these devices are power generator, dynamos, and transformers. Okay. Yes. So see here in which way magnetic field can be changed from a circuit, closed circuit. See here, this is a coil, round shaped coil. Okay. This coil is placed in 3D, or you can say in a space, a vertical plane, perpendicular plane to the sheet of paper, right? And here it is a magnet, north and south. So definitely a large amount of magnetic field is emerges from north pole and will back to the south pole. Okay. Now see, the coil having some magnetic lines of forces passing through this coil perpendicularly. Okay. Means some amount of magnetic field is there linked with the coil because some magnetic lines of forces are crossing the area of the coil. But you make the this magnet on moving. Okay, you move this magnet and keep this lines of forces, keep this magnet closer to the coil. Then what will happen? Initially, the flux, let us suppose that the flux initially is phi 1, but when you keep closer this magnet, the flux will be change and it will phi 2, right? Definitely, phi 2 will be greater than phi 1. Yes or no? So does there is a change of flux takes place? Yes, obviously there is a change of flux is equals to phi 2 minus phi 1, right? So as there is a change of flux, so definitely there will be a change of magnetic field because for phi 1 flux, suppose magnetic field B1 is encountered by this loop. For phi 2 magnetic field B2, okay, is encountered by this loop. Okay. So there is also change in magnetic field. Yes or no? That is equals to B2 minus B1. Clear? Change in flux. Second thing, so if you change the flux, so there is a change of magnetic field. As a result, there will be a production of EMF. What is EMF? EMF means polarity. Like if this terminal of coil or loop become positive, then another one will become negative. Okay. Oh, it may be there key. It may be if it is negative, then the another will be positive, surely. But they having the opposite polarity, right? Okay. So this is called induced EMF. Okay, it may be of 1 volt, it may be of 2 volt, it may be of 3 volt. Okay, but there is some voltage, some EMF will develop across these two terminal. This EMF is called induced EMF. Understood? Okay, so this is called induced EMF. But if you connected this coil, these two terminal with the help of a wire or shorting by a bulb, using a bulb, instantaneously the current will flow and the bulb will glow, right? Yes, so there is induced current. Okay, so till you have not connected these terminals, there will be only induced EMF. But after, but once you connected these terminal or close this circuit using any conductor or any resistance or any type of element, then there will be a what induced current also. Understood? So two things are there: induced EMF and induced current. Any doubt? Okay. Next topic is magnetic flux. Yes, magnetic flux. What are magnetic flux? Okay, different things. One is magnetic lines of forces, and second is magnetic flux. Okay, Two things are there. First is magnetic lines of forces, and another one is magnetic flux. Okay, magnetic lines of forces are the closed imaginary smooth curve upon which a unit north pole can move freely. Right, beta? Unit north pole can move freely. Yes, these are called magnetic lines of forces. Okay. Now, if you bring coil here, a loop here, a loop here, like this is a loop, circular loop. Okay, and you have thread this one loop with some wire or some thread. Okay, this loop is suspended. Okay, so what you see, the number lines of forces are entering from left end and emerging out, exiting from the second end. Right, beta? Some lines of forces are entering and some are exiting. Right. So what are magnetic flux? Does these all the lines contributed as a flux? No. Only the lines of forces which are perpendicular to the area, perpendicular to the surface, right? Only the number of lines of forces passing perpendicular to the surface. Like see here, this is our surface. Okay, this is our surface. So if I say there are two lines only, two lines, those are passing perpendicular to the surface. Clearly, you see here, these lines are passing perpendicular to the surface. Okay, so these lines are contributed as magnetic flux. Okay, so what is magnetic flux? The number of lines of forces passing perpendicular to the given surface are called magnetic lines of forces. Understood? Yes. If there are thousands of lines which are passing parallel to the surface, means not crossing the surface. Okay. If you say what amount of flux will be contributed here, here it is equals to zero, right? Flux here equals to zero. Why? Because none of the line is passing perpendicular to the surface. All are parallel to the surface, means no flux will be contributed. Clear, beta? So the number of the water magnetic flux, the magnetic flux through any surface held in a magnetic field B is measured by the total number of magnetic lines of forces crossing the surface normally. Yes, only those lines will be taken which are crossing the surface normally. Clear or not clear? Yes. So crossing the surface normally. Yes, see here. This is our surface. Okay, beta? This is our surface having area A. The surface having area A. Clear? And this surface is kept in a magnetic field B. Okay? Throughout uniform magnetic field is B is there. Clear or not clear? Okay. Throughout magnetic field B is there. Yes. B vector. So amount of flux phi is equals to answer. See here, if this area is considered as 1 meter square, so from one point the intensity, the magnetic field is passing B vector. So from the whole area, the amount of flux can be given as B into A. Yes or no? From one point, if the magnetic field passing is equals to B, okay, from one point. So by the total area, the total amount of flux equals to B multiplied by A, right? You make it A times, so you will figure out all amount of flux now passing through that surface. Understood or not? Yes. So phi is equals to B into A. So this is supposed to be the maximum flux when it is passing normally to the surface, phi max equals to B into A. Note it. Clear? Okay, so this is equals to B into A. Okay, now next, take a different case here. Like first I talk about the area vector. Look in the previous case, if I talk about area vector in the previous case, then area vector is towards the normal of the plane of sheet. Okay, and the area vector is given by n cap. N cap is the area vector. Clear, beta? The direction of area is perpendicular to that surface. Okay, see here, for maximum flux, the angle between the theta is the what? Theta is equals to angle between B vector and N vector. Clear, beta? So here the angle between B vector and N vector equals to 0 degree. Yes or no? Theta equals to 0 degree. Right? Hmm. So check here. If magnetic field is passing through this way, like this, here it is a point and magnetic field is passing in this sense. It just penetrate and passing through this. Other way, okay. Means the field is oblique, passing oblique. It is not perfectly normal to the surface. It is oblique to the surface. Let us draw here n vector. Okay, n cap, the area vector. Yes, this is area vector, n vector or n cap. Okay, clear. And this is what? This is B. Now this magnetic field is not perfectly perpendicular to the surface. Okay, it having some angle with the area vector. Okay, this angle is theta. Clear or not? Okay, and the total area of this body is equals to A. This surface equals to A. Clear, beta? Now you can resolute B into components, rectangular component. Along the theta in physics, if there is a vector R or component R, not necessarily vector, magnitude is R, then along the direction of theta, the component equals to R cos theta. Clear? And perpendicular component is equals to R sin theta. Right? So here it will be in the direction of theta. The component of the magnetic field will break out, that is equals to B cos theta. And parallel to the sheet, the component is equals to B sin theta. Right or wrong? B sin theta. Clear? Now take a small area surrounding to that point. Yes, this one area. So suppose this area having magnitude as ds, right, beta? So the amount of flux d phi is equals to, look here, what is the magnetic field? It is not completed B, crossing normally to the surface. Here it is only B cos theta passing normally to the surface. Yes or no? So in place of B, you have to take B cos theta, right or wrong? In place of B, you have to take B cos theta, because in the previous case, the vector B is passing normally to the surface everywhere. So whole the amount of B is contributed as magnetic flux, right? But here B cos theta, the normal component of the magnetic field, is contributed as flux. So d phi is equals to B cos theta dot a smaller area ds, right, beta? So B cos theta into ds. This is the small flux. Now, if you want complete amount of flux from this surface, what you need to do? Phi net is equals to integration of d phi, right, beta? So phi net is equals to integration of d phi. So phi net total flux is equals to what? B cos theta into ds. Okay. So net flux equals to B ds cos theta. Okay, b ds cos theta. So phi net is equals to b ds cos theta. Now phi net equals to, can you write this one as b dot ds? Very sure. Why b dot ds? Because a dot b equals to, by the formula of dot product, a dot b equals to mod of a mod of b cos theta. Yes or no? So if we remove this, eliminate this cos theta, means by reverse approach, from see the formula from right to left, so it will become a dot b. Yes or no? So b dot ds, this is called total flux. Okay. Yes, total flux equals to b dot ds. Done. Okay. So this is amount of total flux. Yes. See, sigma is used for discrete distribution. Okay, and for continuous distribution, it is integration of b dot ds. Okay, when you're using sigma, this means you considering the point to point, point to point, point to point as a discrete distribution of any quantity. But for integration, there is a closed everywhere. Okay, for this closed bounded surface, b dot ds integration. This is total flux, right? Yes. So so two formulas are there. Phi max equals to BA, and this is the most important formula for all type of geometries, that is equals to phi B dot ds. Clear? Yes. For regular for regular surface. See, you have seen phi is equals to net flux. Phi is equals to B dot A. Total flux phi is also equals to B dot A, right? So phi is equals to BA cos theta. Yes. Phi is equals to BA cos theta. ठीक है ना? For regular bodies, like we have seen, we have taken a rectangular sheet like this, having area A. Okay. And the magnetic flux is crossing like this. This is magnetic field B vector, right? So again, the same thing. The component that is along the normal vector will be equals to b cos theta. Clear? So from the total area, total flux from the complete area, if one point carries a field of b cos theta, then the total area will carry a field of how much? Phi is equals to b cos theta multiplied by a. So this is equals to total flux, phi equal to b cos theta into a. Same thing is written here, that is equals to ba cos theta. Yes or no? So phi is equals to net flux equals to BA cos theta. This is total flux. Okay. In dot product, you can write this one. Phi is equals to B dot A. Okay. So where you can apply this formula? For regular geometry like rectangle, right triangle. Okay. It means for geometries you having the formula for area. Okay. So for regular geometry, you apply this one formula. But for non-regular geometries, okay, this one, sorry, this one, phi net is equals to b dot ds. Important. Okay. VIMP. Yes. Yes. So phi is equals to b dot a for regular geometry. Regular geometry or for vector form. You when you have given the things in vector form. Okay. As you have dot product, you have to make a dot product. Yeah. So this is completed. Phi is equals to ba cos theta. Yes. Now, you see here, correct? This is a b vector and this is area vector, always perpendicular. Okay. So if you break b vector in the direction of area vector, then the component equals to b cos theta, right? So only the b cos theta component will be contributed as a flux. Okay. Now, if the coil having N turns. What I am saying here, try to understand. Like there is a loop, like this is a loop, okay? And flux is passing, magnetic field is passing like this. This is magnetic field. Clear, beta? And this is the direction of area of loop, that is equals to n vector. Clear? So here is theta angle. Now, if I'm talking about the area of the loop is A, if the total area of the loop is equals to A, so the total flux is equals to B dot A, right? BA cos theta. B dot A is equals to BA cos theta. Okay. B dot A. As loop containing only one turns. Okay. But if the loop containing n turns, okay, beta. If the loop containing how many terms? N terms. Take it capital N because small n is reserved for solenoidal case. Small n equals to capital N by L. Okay. So for n turns, the flux will be associated with the n number of loops because there are too many loops. Yes or no? So for n terms, the total flux will be n times of the flux link with the one coil. So phi net for n terms becomes nb dot a. Yes or no? It will become n times of b dot a. Moreover, if you open it, it will give you mod b mod a cos theta. Yes. So for n terms, there will be equals to nba cos theta. Understood? Clear or not clear? Yes, when theta is equals to 90 degree, what theta? Theta is the angle between normal, normal direction. Here it is normal direction and magnetic field. When theta is equals to 90 degree, then the flux equals to 0. Okay. When theta is equals to 90 degree, then the flux equal to 0. Yes. Look here the case of theta equals to 90 degree. See, this is our area vector. Sorry, area sheet. So towards this direction, there will be area vector, right? And magnetic field is passing through this like this. So this is the direction of magnetic field. So does there you see any type of you can say penetration of this sheet by this field? No, nothing penetration is there. It's just touch and go. So here, what is the angle? Tell me what is the angle, beta? Theta is equals to 90 degree. So B and the angle between B vector and N vector equals to 90 degree. Okay, so amount of flux equals to what? 0. Clear or not clear? Amount of flux here equals to 0 because B and N vector are perpendicular to each other. Okay, right? Second thing, if theta is equals to 0 degree, I already have concluded about this. When theta equals to 0 degree, then phi is equals to BA, that is equals to maximum value. Okay, we already have seen this. Theta is equals to 0 degree. Then flux is equals to maximum. Phi max equals to B into A. Theta equal to 0 degree. Clear, beta? So this is theta equal to 0 degree. Now talking about the unit of magnetic flux. So formula phi is equals to B into A. Phi is equals to vector B dot vector A. Right, beta? So B means Tesla and A means meter square. So unit of magnetic flux is equals to Tesla meter square and commonly it is called Weber. Clear, beta? It is called Weber. So the SI unit of magnetic flux is Weber. Okay. SI unit of magnetic flux is Weber. Yes. Okay. So what is 1 Weber? Next question is 1 Weber. Define 1 Weber. Okay. So we have seen this phi is equals to B into A, B dot A. Right, beta? If you open it, phi is equals to B A cos theta. So to define it 1 Weber, what you have to do, take everything as unity means 1. Yes. Okay. So if there is a magnetic field of 1 Tesla, yes, you have to take B is equals to how much? 1 Tesla. And area of the coil is equals to 1 meter square. Area of the coil equals to 1 meter square. And cos theta equals to 1. But when, my dear, cos theta is equals to 1 when theta is equals to 0 degree. Okay. Means your area is kept perpendicular to the field. Yes. Here you see this is n vector and the magnetic field is perpendicular to the plane of area. So here angle equals to 0 degree. Then the amount of flux from that sheet from that area equals to 1 Weber. Right or wrong? So 1 Weber is the amount of magnetic flux over an area of 1 meter square held normal to a uniform magnetic field of 1 Tesla. Yes. 1 Weber is the amount of magnetic flux over an area of 1 meter square held normal to the uniform magnetic field of 1 Tesla. Okay, clear or not clear? So 1 Weber is the amount of flux when your coil of having 1 meter square area kept in a field of 1 Tesla perpendicular to the magnetic field. Clear or not clear? Yes. Once again, like you having a coil, this one coil having area 1 meter square. Okay. Look, this one coil. This is a circular coil. This circular coil having an area of 1 meter square. And this is magnetic field. Like here it is a magnetic field just penetrating the field, the coil. So here the magnetic field B is having magnitude 1 Tesla. Right, beta? Now check about the direction of magnetic field with the normal vector. Definitely the normal vector will lie here perpendicular to the field. Now you see the magnetic field is just perpendicular to the surface as the lines of forces are penetrating. Yes or no? So theta is equals to how much? 0 degree. Once again, remember here is the theta is the angle between normal vector and B vector. Okay. So as the normal vector is aligned with the B vector, so theta is equals to 0 degree. So take the amount of flux. Phi is equal to formula B dot A. Okay, so phi is equals to B A cos theta. Put the values. Phi is equals to B means 1 Tesla. A means 1 meter square. And cos of how much? How much degree, beta? Speak up, please. Theta equals to how much? 0 degree. B is parallel to N. So it will be equals to 0 degree, right? So cos 0 equals to 1. So 1 into 1 into 1, answer equals to 1 Weber. Understood? So this is the amount of flux here is equals to 1 Weber. Okay. Question may be asked, define 1 Weber. So 1 Weber is the amount of magnetic flux over an area of 1 meter square held normal to the uniform magnetic field of 1 Tesla, right? So 1 Weber equals to 1 Tesla into 1 meter square. Yes, magnetic flux is a scalar quantity. Yeah, definitely. These are the number of lines and number is a scalar quantity. Clear? So magnetic flux is a scalar quantity. One more thing, dot product is also called a scalar product. So this quantity magnetic flux is made up of by the scalar product of two vector quantities. And the scalar product of two vector quantities is always a scalar. So magnetic flux is a scalar quantity. Clear, beta? So magnetic flux is a scalar quantity. Now, when a body is present in a uniform or non-uniform magnetic field, outward flux is to be positive, while the inward flux is taken negative. We already studied this concept in the magnetism. Like there is a loop and lines of forces are going like this. So the magnetic lines of forces, the flux contributed via this line is taken as negative as the lines of forces entering to the surface area, right? And from here it is going emerging out from the loop. So flux is equals to positive. Okay, clear? So total flux is equals to 0. Total flux equals to 0 because the number of amount of flux entering is equals to amount of flux exiting through a coil. Okay, this is a very important question we have read in the previous topic. Why the amount of flux is equals to 0 through a loop, right? So total flux from any loop phi is equals to 0. Maybe you remember we have so many times we have seen such a question. Okay. Okay, so this is completed. Inward flux is taken negative and outward flux is taken positive. Okay, talking about the experiment of Faraday and Henry. Yes, let us talk about electromagnetic induction. Hmm. So, as I told you, uh, when there is a current loop, okay, like this is a loop placed in 3D, and you moving a magnet towards the loop, right? Okay, so there is a production of EMF. EMF means voltage polarity will be developed. Now, there is a question in your mind, sir, does there is a plus or minus here? Or second situation here, it can be plus or minus. Which one will be the correct? Okay, perhaps you think about this. So, see in what way we can generate the polarity of this electricity, or you can say EMF. This answer is given by Michael Faraday's experiment. All these answers can be given by Michael Faraday's experiment. Okay. So one by one, we see all the experiment done by Michael Faraday, then Henry. So experiment number one. Then after performing all the experiment, we will give a very important, most important law, that is called Faraday law. Faraday's law. Okay. So Faraday is given two laws. First law is what? First law means till time you will change the magnetic flux. Okay, till time. Only up to that time there is a production of EMF. As you stop changing EMF, their EMF will be, as you stop changing the flux, stop changing the flux, the magnetic field will be, the electric field will be zero. Okay. Second, the EMF produced is directly proportional to rate of change of flux. As fast you changing the amount of flux through the coil, greater will be the EMF produced in the coil, right? Mm. Maybe you have performed some scientific experiment in school, earlier school, 7, 8, 9. There is a production of electric current, and you taking a small dynamo and rotating this disc. Have you performed such like experiment? If you have rotated the disc, then there is a LED glow of LED like this. Yes. Have you performed this experiment? Okay. So many small projects are there that will give you an idea of this Faraday's second law, that the EMF is produces, the amount of EMF produced is directly proportional to rate of change of flux. The maximum, the rate of change of flux will be there, the maximum of EMF will produce. Let us see by Faraday's experiment, experiment of Faraday's and Henry. Experiment number one, current induced by a magnet. Current induced by a magnet. Okay. Yes, see here, take a coil is there and take a magnet is here. Yes. Figure shows a coil or loop C. Yes, here it is given a coil, or consider it as a loop of C. A few turns conducting material insulated from each other. Yes, all the terms are insulated from each other. It is connected to a sensitive galvanometer G. Faraday and Henry observed this. Yes, see here, this is a coil, and like this, we have closed these connections. Okay. So what observed it? If you keep this north pole closer to the coil, clear beta? If you keep this north pole closer to the coil, then when north pole of the bar magnet is pushed towards the coil, The galvanometer shows a sudden deflection, which indicate that current is induced in the coil. Yes. You tell me when you started this magnet keep closer to the coil, the magnetic flux will be rapidly increasing. Say yes or no. Magnetic flux will be increasing. Yes or no. So as the magnetic flux will be increasing, there is a change of flux. Agree? Flux is continuously increasing. Okay. So till the time the flux is changing, induced EMF will produced here. EMF will produce here, and a current will be there. Induced current will be there as the circuit is closed using a galvanometer. Okay. And galvanometer is a device which can detect very minute amount of current. So definitely the galvanometer pointer will be deflect in some direction, right? Now talking about the direction of current. See here what will be the direction of current. Okay. After some time we will study there is a Lange law, and according to the Lange law, if you keep this north pole towards this coil, then by the Lange law, the very first turn and all very first turns become left, which is facing the magnet. Okay, like here it is facing the magnet. Clear, but clear, beta. So it is become north. It is become north pole, right? Now align your current, or you know कि N for anti. Anti is my trick. Anti means anti-clockwise. Anti means anti-clockwise. Clear or not clear? So very carefully watch this. If there is a north pole, development of north pole, check here the direction of current is like this in this turn. Okay, and here it is in this turn. Clear or not clear? So see, yes, current is getting downward here and is emerging out from the circuit, and likewise it is passing through the galvanometer like this. Clear or not clear? Yes, so this is the direction of current. Okay, okay. And again from the turn that is behind the coil, again it is looping like this and this. Okay, and so the polarity of current will be, yes, question asked in CBSE examination, they will give you 2 points, A and B. And question is saying that if north pole is coming closer to the coil, then tell me the polarity of A and B. Now tell me, A will be positive or negative? A and B. Yes, two choices are there. Either they plus and minus or minus and plus. Tell me what is the correct configuration of the polarity or EMF? EMF. Yes, exactly. As the current is going outward, so there is a battery plus terminal, and here current is entering. So current is entering from the negative terminal and emerging out from the positive terminal. So here it will be plus and minus. Understood? Yes, very important. Okay. So first you see the coil, make the north pole. Kindly align the arrows in the coil as accordance with your north and south. Yes. Especially design north and south, that will help you to identify the direction of current in the coil. Okay. But if you try to learn, N means anti, means if there is a north pole, the direction of current will be anti-clockwise. And S means clockwise. Clear, beta? So this first thing. There is, yes. Second observation. First observation, when north pole of bar magnet is pushed toward the coil, the galvanometer shows a sudden deflection, which indicate that current is induced in the coil. Understood? Means till the time we have changes the flux, there is a current flowing in the coil. Yes. Second observation, there is a no deflection when the bar magnet is held stationary anywhere. Yes, exactly. When you keep the coil with respect to a stationary magnet, then the amount of flux remains same. Flux will be there, but there is no change in flux. Agree, cannot agree? So yes, so there is flux, but no change in flux. But the thing, important thing is change in flux, delta phi. So delta phi, when you keep this magnet stationary, then delta phi equals to 0. And as delta phi is equals to 0, no change in flux, there is no EMF. EMF is also 0. Understood? So yes, there is no deflection when the bar magnet is held stationary anywhere. So what is logic? If delta phi is equals to 0, EMF is equals to 0. Clear or not? Yes. Third case, sorry. When the magnet is moved away from the coil, the galvanometer shows deflection in the opposite direction, which indicate that reversal in the direction of induced current. Yes. In the first case, you keep the magnet towards the coil. But in the second case, when you keep the magnet far away from the coil, yes, means you bring this magnet in the backside direction. Understood, beta? Yes. Now you moving this magnet in opposite direction. Look here, some new concept will be there. Now, if you're keeping this magnet in opposite direction, moving this magnet in opposite direction, you see the number of flux will be continuously decreasing. Okay, because at before it was closer to the coil, and after moving it backward, definitely it will be become away from the coil. So the number of flux will be decreasing. Yes or no? Change of flux is negative there. Okay, change of flux will be negative. Yes, because the flux is continuously decreasing. Now, if this north pole is getting away from the coil, the nearer pole inside the loop will induce as south. Okay, so check here. Previously, the development of North Pole, but here it is now South Pole. Clear, beta? So by the rising of South Pole here, check the direction. It is the direction South Pole. Get aligned with these arrows. Yes or no? So reversing the direction of current. Check. Yes. So here it is upward and here it is downward. Clear or not? So check now the current is entering here. Okay, current is entering here. Understood or not? Yes, current is entering here from this loop. So as the current is entering from this loop, so the direction of current changes and the polarity will reverse. So here it will be plus and it will be minus. Understood? Yes. So polarity of the current on reversing the direction of motion of magnet, the polarity of current is also reverse. Now the galvanometer will deflect in another direction. Okay, previously if it is moving towards your needle of galvanometer is moving towards right, now it is moving towards left. Understood? So when the south pole of bar magnet, uh, sorry, here it is. When the magnet is moved away from the coil of the galvanometer shows deflection in the opposite direction, which indicate reversal in the direction of induced current. Clear, beta? Yes. Next, when south pole of bar magnet is moved towards or away from the coil, the galvanometer deflection are opposite to those observed with the north pole for similar movement. Yes. So same experiment Michael Faraday and Henry performed, but now this time with the South Pole. Previously, they are taken the observation with the North Pole, but now they are taken the observation with the South Pole. Okay, and they have seen the similar results. Okay, the galvanometer deflection and hence induced current is found to be larger when the magnet is pushed toward or pulled away from the coil faster. Yes. First thing what we have seen that induced EMF, amount of EMF is directly proportional to the change of flux. Okay. Greater the change of flux, greater we have seen the EMF. Okay or not? This was the first result, right, beta? Second result is faster you bring the magnet towards the coil. As fast as you bring the magnet towards the coil, more deflection in the galvanometer. Greater deflection means EMF is inversely proportional to change of time. Clear or not clear? As the change of time of movement will be less, EMF will be greater. Yes or no? It is inversely proportional to the time. Clear or not? For the less amount of time, more amount of the EMF will be there. Yes or no? Less amount of time means you moving the magnet faster. If you moving the magnet faster, EMF will be larger. Yes. So the galvanometer deflection and hence induced current is found to be larger when magnet is pushed towards the or pulled away from the coil faster. Clear or not? So we have seen two observation, very important observation. First, E is directly proportional to change in flux, and second, E is inversely proportional to delta T. Now combine them, you will get E is proportional to delta phi upon delta T. What this term is called? This is called rate of change of flux. Am I right? Rate of change of flux. So this is called rate of change of flux. Means EMF produced in a coil is directly proportional to rate of change of flux. Okay, this becomes Faraday's second law. Now next observation, when the bar magnet is held stationary and coil C is moved towards or away from the magnet, the same effect are observed. It shows that relative motion between the coil and magnet is responsible for the induction of electric current in the coil. Yes. Now in the previous experiment, first experiment, you seen that there is a stationary coil or loop, okay, and movement of magnet is moved towards and far away from the coil, right? In the second experiment, Faraday keep the magnet at rest and he moves the setup of coil towards the magnet and far away from the magnet, okay. So you see, every time there is a change of flux, okay, and the matterful thing is the change of flux. Doesn't matter you changing the magnet, you moving the magnet, or you moving the coil. So he get the same result. Okay, previously he moved the magnet, and after then in second case he moved the coil, and he seen the same result. Yes, it shows relative motion between the coil and magnet is responsible. Okay, it is not necessarily you move the magnet only or you move the coil only. Rather, relative motion is important for the induction of electric current in the coil. Clear or not clear? Yes. So relative motion is very important. Now experiment number two. Yes, this experiment, this six observation are very important. Experiment number two we will perform later on. First, we have to see the Faraday's law. Yes. Now, Faraday's law. First law. So, from the experiment, because this experiment, experiment number two, is related with the mutual induction. Okay. Some another thing is there that is called mutual induction. So let us complete the first concept. After then we will move to the second one. Faraday's law. So after the Faraday's experiment, Faraday's has given two very important law of electromagnetic induction. And the whole electromagnetic induction is runs on this law. First law. Whenever the amount of magnetic flux linked with a circuit changes, an EMF is induced in the circuit, the induced EMF exists so long as the change in magnetic flux continues. Yes, clear? The induced EMF exists so long, it will exist up to that time till the time there is a change of magnetic flux. As you stop the change in magnetic flux, As a result, EMF will be zero. But as you continue the change in magnetic flux, the production of EMF will continue. Clear or not clear? Yes. A movie was there, Shah Rukh Khan, Jab Tak Hai Jaan. Okay? Jab Tak Hai Jaan. So this trick means till the magnet is moving or till the coil is moving, so till the flux is changing. And till the flux is changing, there is Jab Tak means till the flux is changing, there is EMF. Okay? Yes. So this becomes a trick. Jab tak hai jaan rule. Okay. Second law. Second law, as I said, produced EMF is directly proportional to rate of change of flux. Right, beta? Yes, E is proportional to delta phi by delta t. So E is proportional to what is delta phi? That is equals to phi 2 minus phi 1. Phi 2 means final flux, phi 1 means initial flux, and time T2 minus T1. This is Faraday's second law. Second law, the magnetic flux of EMF induced is directly proportional to the rate of change of magnetic flux. Very important. The magnitude of EMF produced. Yes, I am not talking about the direction. I am talking about the magnitude. Okay, because the concept of direction is given by another scientist, that is Lange. But Michael Faraday is only given the concept of induced EMF magnitude. Okay, so the magnitude of EMF induced in a circuit is directly proportional to the rate of change of magnetic flux linked with the circuit. That is, induced EMF E is directly proportional to change of flux upon change of time. It will become phi 2 minus phi 1 upon T. Right? So E is equals to, now eliminate the constant here. E is equals to phi 2 minus phi 1 upon T2 minus T1. If you counting your time from T equal to 0 and up to the final time T is equals to T, then T2 minus T1 becomes T also. So E proportional to phi 2 minus phi 1 upon T. Understood this line? From where it came, ठीक है ना? Means phi 2 minus phi 1 upon T. Because generally your starting time is 0 and final time is T. So no need to write every time T2 minus T1. Rather you can take here T minus 0. So it will become T. Clear? So place a value of constant here. E is equals to K phi 2 minus phi 1 upon T. Yes. In all system of unit, the constant K, okay, derived experimentally the value of K equals to 1. So E is equals to phi 2 minus phi 1 upon T. Right? So E is equals to phi 2 minus phi 1 upon T. So change in flux upon change in time. So we have already seen that E is proportional to delta phi upon delta T. Clear? So E is proportional to delta phi upon delta T. In calculus way, you can write E is proportional to d phi by dt. So I'm solving here. As E is proportional to delta phi upon delta T. So E is equals to K delta phi by delta T. And by experiment, E is equals to K, the value of K equals to 1. So it will become only delta phi upon delta T. Clear? Yes, in meaning of calculus, V of calculus, you can write E is equals to d phi by dt. Very, very important, my dear. One numerical will be from this concept, E equals to d phi by dt. The magnitude of EMF can be carried out by this formula. Okay, rate of change of flux or derivative of flux is given by EMF. Clear? Yes. Like example, see, example. From a coil, amount of flux, amount of flux changing with respect to time, changing with respect to time is given by, okay, phi. Amount of flux not changing, it is linked. Okay, Amount of flux linked with respect to time is given by phi is equals to 3t square plus 7t plus 4. This is numerical beta. So phi is equals to 3t square plus 7t plus 4. Find EMF at 2 second. Okay. Estimate the value of EMF produced with a coil at 2 second. You see, flux is depending on time, means as you change the time, the amount of flux will be changed, right? So there is a definitely EMF. Now what we have to find, the amount of EMF, magnitude of EMF. So as we know, the formula E is equals to d phi by dt, right beta? We just have proven E is equals to d phi by dt for the numerical cases. So E is equals to d by dt. Now what is changing flux? Changing flux is given 3t square plus 7t. 3t square plus 7t. Clear? Now perform the numerical calculations. D by dt for 3t square and d by dt for 7t. Okay. Now 3 is the constant. You can take it out. So 3 is the constant, d by dt of t square and d by dt of 7t. So 7 and d by dt of t. The differentiation of time t with respect to time t is equals to 1 and 3 multiplied by 2t. Understood how it came out t square? You know the formula? No. Okay, see here. D by dt, the formula is d by dt t to the power n equals to n t to the power n minus 1. Okay. This one is the formula for differentiation. Okay. So check here for t to the power 2. Okay. What is here? T to the power 2 now. So t to the power 2. What is n here? 2 t to the power 2 minus 1. So it will become 2t to the power 1. That I can write it 2t. Right? So I have written here 2t plus 7 and differentiation of t with respect to t. dt and dt get cancelled out. It will produce 1. Okay. So EMF produce equals to 6t plus 7. Right. But question is for particular EMF at t equal to 2 second. Yes. When the time is 2 second, what will be the EMF? So answer E for t equals to 2. Place the value 2 here. 6 multiplied by 2 plus 7. 6 twos are 12. Okay. Plus 7. How much answer? 19 volt. Okay. Yes. So 19 volt will be the EMF. Clear? Yes. So this is called Faraday's law. Faraday's second law only given the magnitude of EMF produced during electromagnetic induction. Okay. And the Faraday's law, Faraday's magnitude of EMF is given by E is equals to d phi by dt because it has taken the value of constant k equals to 1. Okay. But after some more experiment by physicist Lenz, okay, Lenz have given some corrections in the formula. Okay, Lenz also have performed some experiment and Lenz given a new formula along with the direction of induced EMF. So what Lenz have done? He said that previously E is equals to K d phi by dt. Right or wrong? Hello? So I am saying that we have already developed that E is equals to K d phi by dt by the same Lenz experiment. Sorry, Faraday's experiment. Right? So Faraday suggests the value of K equals to 1. But here the Lenz said that the value of K is equals to minus 1. K equals to what? Minus 1. So E is equals to minus d phi by dt. This becomes the complete formula for EMF. Okay. Now, what minus sign signifies that? Minus sign signifies that there is a contradiction between EMF and change of flux. Okay. If EMF saying north, change of flux saying south. Okay. If EMF saying day, change of flux saying change of flux will say night, day and night. Means the negative sign, the negative sign express that, indicate that. Okay. Indicate that the direction of EMF, the direction of EMF produce, the direction of EMF produce will always opposes the change of flux. Clear or not clear? Change of flux. Yes. Right hand side it is change of flux, and left hand side it is EMF, and minus sign is for opposition. So here the minus sign said that the EMF produced will always opposes the change of flux. Okay? Yes. So if d phi is the small change in the magnetic flux in the small time, then we can rewrite E equals to d phi by dt. Yes, this minus sign came here because of Lenz's law. Okay. So this is after Lenz's law. Yes, this is not Faraday's law. This deduction is taken after Lenz's law. Okay. Faraday's experiment is only up to here. This one, positive d phi by dt. Clear? Okay. Next, negative sign is taken because induced EMF always opposes any change in the magnetic flux associated with the circuit. Yes. Okay. Negative sign is taken because induced EMF always opposes any change in the magnetic flux associated with the circuit. These all the lines are stated by scientist Lenz. So this whole statement is called Lenz law. Clear? Lenz law. In case of a closely wound coil, N turns, change in magnetic flux associated with each turn is same. So the total induced EMF is given by yes. For a single coil turn equals to minus d phi by dt, right? But if there are n terms, same thing will happen n times, right? So therefore will be the total induced EMF equals to what? Equals to minus n times d phi by dt, right? Means what? This is very important. If you increase the number of turn, the EMF will also increases. Yes or no? Because E is directly proportional to N. Yes or no? So if you increase the number of turns in a coil, EMF will be significantly increases. Clear? And the same concept is carried out in the case of transformer. Only one magic is there in the transformer, that they are varying the number of turns. Okay? Yes. So by increasing the number of turns N in the coil, we can increase the induced EMF, right? You can induce your amount of induced EMF, increase your amount of induced EMF just by increasing the number of turns. So when you decrease the number of turns, EMF is also decreased. Amount of EMF is also decreased. Clear or not clear? Yes. Here is a numerical. A circular coil of radius 10 centimeter, 500 tons and resistance of 2 ohm is placed within plane perpendicular to the horizontal component of the earth magnetic field. It is rotated about an axis vertical diameter through 180 degree in 0.25 second. Estimate the magnitude of the EMF and current induced in the coil. Horizontal component of earth magnetic field is equals to 3 into 10 ki power minus 5 Tesla. Yes, this is CBSE, your NCRT book question, very important. Okay, what to find? You have to find the amount of current. So first you have to find the amount of EMF, electromagnetic force. Then after current, I is equals to V by R by Ohm's law. So in the place of V playing here is E upon R. Okay. So first to calculate E and then to calculate current I equals to E upon R. Let us solve this. So, okay, guys, after reading all these entries, we know this is all the entries are here. Now, by the Faraday's law, by the Lenz's law, E is equals to minus n d phi by dt. Okay, that is equals to minus of n change in flux phi 2 minus phi 1 upon change in time delta t. Right, beta? So we will apply this formula. Which one is equals to minus n delta phi upon delta t. So E is equals to minus of n means 500 tons are there. Delta t time is there given. I think it is 25 second now. Yes, time is given here. Sorry, 0.25 second. It is equals to 0.25. Right? Now flux phi 2 minus phi 1. Clear, beta? Now the formula of flux phi is equals to BA cos theta. Yes or no? We have learned this formula BA cos theta. Clear or not? Check here. In the first hour we have completed this. Phi is equals to BA cos theta. Right? So phi is equals to BA cos theta. So B is continuous throughout the process. B is constant, A is constant. Only theta is varying. So for the two cases, for minus 500, you can write here BA cos theta 2 minus BA cos theta 1. Okay, upon 0.25. Fine. Now take B and A as a common because they are constant. So minus 500 multiplied by B multiplied by A. Now cos theta 2, your final angle equals to 180 degree. Am I right? And your initial angle was 0 degree. So divide by 0.25. So cos 180 minus 500 multiplied by B. What it is B? B is equals to given. Yeah, it is given somewhere. I've seen. Yes, 3 into 10 ki power minus 5 Tesla. Okay. So place here 3 into 10 ki power minus 5 Tesla. Okay. Now area, as there is circular coil and circle having the area pi r square, right? So make the area as pi r square. So pi in the place of pi, that is equals to 22 upon 7. Yes, but it has been taken here. 3.14 the value of pi, and pi r square. We have r equals to 10 centimeter. Yes or no? 10 centimeter equals to 10 to the power minus 1 meter, or 1 upon 10 meter. So 10 to the power minus 1 whole power 2, because pi r square. Clear? Now beta, at denominator it is 0.25. Now value of cos 180, this is equals to minus 1, and cos 0 equals to 1. So minus 1 becomes minus 2, and this minus 2 will cancel this minus sign. And finally, you have the answer of EMF as how much? 3.8 into 10 to the power minus 3 volt. Clear? 3.8 into 10 to the power minus 3 volt. This is your EMF. Now they inquire about current. So you know I is equals to V upon R, but in the place of volt is here, it is EMF upon R. So 3.8 into 10 to the power minus 3 volt, divide by what is resistance? Resistance in here 2 ohm. Clear, beta? So 3.8 divided by 2, 19 to the 38. So it will become 1.9 into 10 ki power 3 ampere. And 10 ki power 3 ampere is called milliampere. So it will become 1.9 milliampere. Right? So 1.9 into 10 to power minus 3 ampere. It is become. As you wish, you can also, you are right, ampere minus 3 ampere or milliampere. No problem at all. Okay. Okay, the second question is also very easy. You have given flux. Just to find the derivative of this flux using the formula E is equals to minus d phi by dt. And they inquire the amount of EMF at t equals to 5 seconds. So thus place the value of t is equals to 5. Right? Okay. So now we have completed here Faraday's law by using a magnet and a coil combination. Yes. Now we are going to Lenz's law. Okay, we already have seen that Lenz's have given the direction of this minus sign. E is equals to d phi by dt till the time of Faraday, but Lenz has introduced this minus sign. But it is not easy to produce this minus sign in a single side. There was so many experiments performed by the Lenz. So let us perform those experiment Lenz law after learning this Lenz law. So learn Lenz what said. Lenz said about this negative sign. Okay. Lenz said that the direction of induced EMF or nature of induced EMF, okay, the direction of induced EMF is such that in such a way, you can say the induced EMF is produced in such a way, it always poses the change of flux. Clear? The induced EMF natures is such that it always poses the change in flux. Clear? Who create the EMF? Change in flux creates the EMF. And the EMF always opposes to its creator, that is change of flux. Okay. So let us read this one in professional language. According to the Lenz's law, the polarity of the induced EMF, yes, the polarity of induced EMF, plus and minus, yes or no? So plus and minus polarities of EMF induced is such that it opposes the change in magnetic flux responsible for its production. Understood? Means the EMF, the nature of EMF is such that the polarity of EMF is such that it always opposes its creator, or it always proposes the change in magnetic flux that is responsible for its production. Understood? This law gives the direction of current induced in a circuit. Yes, this law gives the direction of current induced in a circuit. Like in the last experiment, Faraday's experiment, I told you the direction of current. Yes or no? You see here in this one experiment, I told you the direction of current. Like clause, the polarity of the this circuit will be -2 plus and +2 minus, like that. Okay. So what I have followed, I have followed the Lenz law. I have followed the Lenz law. But now I will tell you about the position. Okay. Till now we have not talked about the position of the change in flux. But now we are in situation to talk about the opposition. How? See, in the first case, your magnet is coming towards the coil. Yes or no? In the first case, your magnet is coming towards the coil. Yes, see here. Your north pole is coming towards the coil, right? So this coil will develop that pole which will opposes the change of flux. Means this coil will develop north pole to oppose the neighboring north pole. Yes or no? Hey, Mr. North, don't come close to me. Okay. So the coil will generate a north pole. Understood? Because the flux is changing because of uh, coming closer of north pole. Okay. To oppose that, this coil will generate north pole. Okay. And accordingly, the direction of current will be here anti-clockwise. Understood? Yes. Now, second thing, when this magnet going away from this coil, yes, see here, when this magnet is going away from this coil, so continuously the flux will be decreasing. Yes or no? Now, the coil do not wants to change of this flux. The coil want the flux as it is. There is no change of flux. So the coil will develop south pole. Okay, because it opposes to becoming north pole far away. Okay, it opposes the uh, this north pole should not move. Okay, so the coil will generate south pole to attract this north pole. Please don't go. When it is coming closer, the coil saying, hey, do not come towards me. But when it is going away from the coil, it is saying, please do not go. I am south. Stop there. Yes or no? So the polarity will be clockwise. Understood? So polarity will be clockwise, and the direction of the current will be changed. Okay. So in such a way, the polarity of the induced EMF can be calculated using Lenz's law. Okay. And only the concept is that the direction of the polarity of induced EMF is such that it always opposes the change in flux. Okay. Explanation. Yes. When north pole of a bar magnet is being pushed towards the coil, what we have read, just we have read here, same concept is mentioned. North, yeah. The north pole of the bar magnet is being pushed towards the coil. The amount of magnetic flux linked with the coil increases. Yes or no? Current, okay, increases. So current induced, but before the current, the voltage induced. Okay, the EMF induced. So the EMF induced in the coil is such that it opposes. Okay, what to oppose? Oppose for coming nearer of north pole. Okay, so it will develop a north pole. So current is induced in the coil such a direction that is opposes the increase of flux. This is possible only when the current induced in the coil in anti-clockwise direction. Yes, only you can offer a position towards this north pole by this loop when there is a development of north pole. Yes or no? And we have learned about magnetic pole that when there is a flow of current in anti-clockwise direction, then there is a development of north pole. Okay. So if north pole is comes closer to the coil, then the induced current will be developed in the anti-clockwise direction. So it will make a dipole. The front part of the dipole that is facing towards the magnet will be a north pole, right? We have learned in chapter number 5 that magnetic current carrying loop is behave like a magnetic dipole. Yes or no? And if the current is flowing in the anti-clockwise direction, this pole become north and the behind one pole becomes south. Yes or no? So current will develop in the anti-clockwise direction. Same thing is mentioned here. So current is into the coil is such direction that it opposes the increase in flux, means position of north pole. This is possible only when the current is induced in the coil in anti-clockwise direction with respect to the observer on the side of the bar magnet. Clear, beta? Yes, see here. So this is a north pole, development of north pole here. Like north pole is coming closer to the coil. So here is the development of north pole. Okay, anti-clockwise direction developed here. So the galvanometer moved in one direction. Clear? Now, second case, movement against attraction. Yes, see here, the north pole is moving towards out of away from the coil. Now, if magnet is moving away from the coil, the correct the direction of current such that should be in that direction that it's produce a pole that is opposing this you can say motion. Okay, opposing this motion. So if the north pole is going outward far away from the pole, so there should be need of development of south pole, so the current in clockwise. Understood? So this is on, and now this time as the current is clockwise, so deflection, the direction of deflection will be reverse here. Okay, so similarly, when north pole of the bar magnet is moved away, yes, we are talking about the second case, away from the coil, the magnetic flux linked with the coil decreases. Yes, we have seen when the coil is getting away from the magnet, so the number of flux will be lesser and the flux will be decreases. To oppose this decrease in magnetic flux, current induced in the coil is the clockwise direction. Okay, so when the current will induce in the clockwise direction, this pole becomes south, and south pole and north pole attract each other, so it will oppose getting apart from the north pole. Understood? So its face towards the bar magnet becomes south pole. This would result as an attractive force which opposes the motion of magnet and the corresponding decrease in the magnetic flux. Clear? So in such a way, the direction of magnetic field, sorry, direction of current you can determine. Okay. Now a question is there in your book. Identify the direction of current. Yes, there is a loop. Okay. A magnet, here it is north pole. Yes, some example is there, I think so, in your book. Okay. Yes. See here, a magnet is fall under the effect of gravity, right? Yes. A magnet is fall down under the effect of gravity. Like gravitational acceleration is g. Now, when it comes closer to the coil, tell me what is the acceleration nearer to the coil here? Greater than g, matlab g dash is greater than g dash is less than g, and g dash equals to g. New acceleration will be what? Tell me. Coil, when the coil comes closer, uh, like, yes, first you make this coil like here. Okay. So first it was out of the loop, but when it comes closer to the loop, definitely the flux will enter in the coil. Now what happened? Three cases or four cases is none of these. Tell me. You see, as the coil comes closer, yes or no? So flux will be changed from this coil, yes or no? Lenz's law will apply, and this coil will oppose the changing of flux, means it will develop the current such a way that it opposes the uh, becoming this magnet comes closer. Okay. Okay, so it will develop. North pole is here, so definitely north pole will be developed here like this. So the anti-clockwise current will flow through the coil. Okay. So one thing identified, we have identified that the direction of current is anti-clockwise. Clear or not clear? Now, if this is north pole and this upper face of this dipole is equals to north pole, right? So north and north repelling each other, yes or no? So there is a not only gravitational force, a magnetic repulsion is also working there. So the force they repelling each other. So the net acceleration will be decreased than the previous one. This means answer. The new acceleration will be less than the only gravitational acceleration. Clear or not clear? So new acceleration, sorry, it is less than, not equal. It will be less than the original acceleration, right? Now talking about polarity, if there is a polarity sign of two battery plates are provided there, A and B, 2 points are provided there. Now tell me what is the polarity of A and B? Does it plus and minus or minus and plus? Will it be plus and minus or minus and plus? Exactly. Current is getting out of here, so point B terminal, so it will be plus, and current is entering through the negative terminal, so it will be minus, right? So in this way, you can assign the polarity. This is completion of Lenz law. Now Lenz law and energy conservation. See here, guys. First is electromagnetic induction. Definition we have seen. Then Faraday's law completed. Induced EMF completed. Induced current we have completed. Then Lenz law. Okay. After then only one topic is left in this chapter, self and mutual induction. Okay. And now we are continuing with Lenz law. So about Lenz law, important thing is Lenz law and energy conservation. Okay. A natural question is there. Okay, sir, this is a coil. If this is a coil, yes. Look, this is a coil, and here it is a magnet. See, there is no connection between magnet and coil, no physical connection. Then in what way this current will produce? Like is if it like current will produce like this here, anti-clockwise direction. Clear? But sir, how? If there is no connection between the magnet and this coil, then what type of energy conversion takes place and in which way this current will produce? This is the question. What conservation rule this mechanism does follows? So what is happening there? See, in which way this current is created. Okay. See, actually, when you make this magnet closer to the coil, some effort is needed. Like there is a hand, your hands. Yes or no? You keep this magnet, grab this magnet with your hand and just moving towards this coil. Yes or no? This means some type of mechanical work is there. Exactly. This mechanical work is there. Now, as the flux is continuously changing, passing through the coil, yes or no? So there is changing flux. Changing flux will result the development of North Pole. Exactly, development of North Pole. In against of this North Pole, you have to do some useful work. Yes or no? You have to do some useful work because like you keep your magnet, you move your magnet up to here, then this means from here to there, you have done some amount of work. Yes or no? To overcome this repulsion. Exactly. Repulsion is working there. So to counter this repulsion, definitely you have to do some work. Yes or no? Now this work is reflected here in the form of current. Yes. That is nothing but your work. Okay. So your mechanical work is reflected here as an electrical energy, right? So your mechanical work get expensed here in the form of electrical energy. So it is simply mechanical energy is converted into the form of electrical energy. Clear, beta? Hmm. Electrical energy. Yes. So this is electromagnetic induction. Here the mechanical energy, mechanical work is converted into the form of electrical energy. So which concept the EMI process follows? It follows the law of energy conservation. Okay. It follows the law of energy conservation means Lenz law is in accordance with law of energy conservation. What I said, it is written there in the theoretical form. Lenz law and energy conservation. Yes. Lenz law is in accordance with the law of conservation of energy. Explanation. In the experimental verification of the Lenz law, when north pole of the magnet is moved towards the coil. Yes. When the north pole of the magnet is moved towards the coil, the upper face of the coil acquire the north polarity. Yes or no? Yes. Therefore, work has to be done against the force of repulsion. Yes, we have done this work. And the same work is reflected here as an amount of electric current. Yes, against this force of repulsion in bringing the magnet closer to the coil. Similarly, when the north pole, when the north pole is magnet is moved away from the south polarity, when the north pole of the magnet is moved from the coil, like here in the second experiment, like we have moved the north pole away from the coil. So away from the magnet. So south polarity developed on the upper face of the coil. Yes, the south polarity. So work has to be done against the force of attraction. Yes or no? In both cases, you have done some work. First cases to counter this repulsion. In the second cases, you to counter this attraction in taking the magnet away from the coil. Right? Yes. It is the mechanical work done. Yes. In moving the magnet with respect to coil that changes into the electrical energy. Same thing I said you. Here the mechanical work converted into the electrical energy. Yes or no? It is the mechanical work done in moving the magnet with respect to the coil that changes into the electrical energy producing induced current, right? So this electrical energy that creates because of the expense of mechanical work, so that generates the electrical energy, and that electrical energy is seen in the form of electric current. This electrical energy being transformed only. Okay, so there is exact energy transformation takes place. When we do not move the magnet, work will be zero. Yes, obviously, you keep your magnet as a stationary, there is no movement, so your work is equals to zero, and there is no production of EMF. Yes or no? Induced EMF will be zero. This means it is exact conversion of um, conversion of mechanical work in mechanical energy in the form of electrical energy. Clear, beta? Next is Fleming right hand rule. Yes. For what purpose we are reading Fleming right hand rule? Fleming right hand rule is used to identify the direction of electric current. Yes. To identify the direction of electric current. Yes. Induced current. Okay. Direction of induced current. Induced current. Yes. So let us read Fleming left hand rule. Fleming left hand rule gives us the direction of induced EMF and induced current. Because as you have induced current, then just place plus and minus and you will have the induced EMF direction. In a conductor moving in a magnetic field. In a conductor moving in a magnetic field. Right? Yes. So if we stretch our first finger, that is pointing towards the magnetic field, central finger or middle finger, and thumb of our right hand in mutually perpendicular direction, such that first finger point along the direction of the field and thumb is along the direction of motion. Direction of motion means direction of force, right, beta? Of the conductor. Then the central finger would give us the direction of current, right? Then the central finger would give us the direction of induced current. Yes, see here by practical demonstration. Like there is a magnetic field. This is a north magnet and this is a south magnet. Okay, so convey a electrical, sorry, an invisible magnetic field here. So see a direction also there. Yes, this is a magnetic field B from left to right. Okay, beta. But remember, this is a flat magnet, cannot produce a uniform magnet. Only polar magnet will generate a pattern of uniform magnet. Yes, such like magnet. Clear, beta? Okay, so you have to take the radial magnets. Yes. So this is north and this radial magnet is equals to south. Now a coil is here. Yes, a coil is here. You have applied a force that to make this coil like this in perpendicular plane. Yes, to clockwise. Okay, this is clockwise. Clear? You are rotating this coil in clockwise direction. Now tell me the direction of current here in AB branch. Thus the current direction is A to B or B to A. Okay. Yes. Tell me the direction of current. In what direction the current will be flow in AB? Okay. A to B or B to A. See here how we can figure out the direction of current. First, take your left hand. Sorry, very sorry. Take your right hand as we have to find the direction of electric current. Yes. Now point your first finger in the direction of right side because the magnetic field is given right side. So your forefinger in the direction of magnetic field. Right? Now thumb is entering your plane inside the plane. Yes, thumb is just in interside of your screen, inward. Because the coil is moving this one like this direction, so the this face will getting inside. Yes or no? Yes, yes. So inside the plane. Now check your direction of middle finger. It is going up or down? No, 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 no. Something is wrong. You using your left hand, I think so. Right hand only. See, first your finger is here. This is your index finger pointing towards the right of your laptop screen, right? Your thumb will be penetrating your um, laptop screen inside, okay? And your current will be downward or towards your side. Then your current will be downward, right? Yes, current will be downward. So guys, this is the direction of electric current, downward. Okay, so in this way, current is flowing from here to here. So in this way, you can find the direction of electric current, induced current, using Fleming right hand rule. Clear? Now this question. Check here this question. A magnetic in the given figure, a bar magnet is quickly moved towards the conducting loop having a capacitor. Predict the polarity of poles A and B. Okay. Yes. Tell me the direction of, tell me the polarity of pole A and B. Either plus AB or it is minus A plus B. Check which one will give you the correct polarity. B is plus. Mm. B is plus. See here. Like magnet is north here. So north pole will develop here. Right or wrong? Facing from this side, a north pole will be developed here. Yes or no? So current will be emerging out from A and entering from B. Yes or no? So A will be plus and B will be negative. Right? So here the north pole is approaching the magnet. So induced current in the face of loop is viewed from the left side. So current will flow in such a way that it will behave like a north pole. So the south pole developed in the loop when it is viewed from the right hand side. Yes. So this pole will be north, and if you see from this side, then the behind one pole will be the south pole, but it is not possible to see here because only we have to face this one, the front one. Okay. Yes, so the flow of induced current is clockwise. The flow of induced current in clockwise. But where clockwise? If you see from the right of the coil, it will be clockwise. But if you looking from the this one, left of the coil, it will be anti-clockwise because north pole is facing here, right? Yes. So hence A will acquire positive polarity and B will acquire negative polarity. Clear? So A will be positive and B will be negative. Done? Okay, students, coming to our next derivation, that is about motional electromotive force. So our motive is to change of flux. Okay, what is flux? All total phi is equals to B A cos theta, right? Because phi is equals to B dot A. Okay, phi is equals to B A cos theta. Moreover, you can take phi is equals to n, containing n terms. So phi equals to n B A cos theta. Clear? This is the complete expression for flux. Now, EMF is equals to minus of d phi by dt by Lenge's law, right? So if you place here d by dt and inside the bracket NBA cos theta, then check in how many ways you can develop your EMF. Because this term d by dt means changing with respect to time. And these are the parameters you can change. Yes. So first, if you changing number of terms, EMF can be developed. Okay. Means you can change number of flux. So it depends on dn by dt, keeping all the things remaining constant. So E may be depend on rate of change of number of turns. Otherwise, E also depending on change of magnetic field. You can also change the magnetic field. Third, E can also developed by changing loop area, dA by dt. Right, beta? Loop area of the loop. And last, E is proportional to d cos theta. Means in what variation? You will vary the theta. So E is proportional to d by dt, variation of the angle. As the theta will vary, the cos theta will also vary. So this is cos theta. Okay. So in four ways you can develop your EMF, right? First by varying number of terms, second by varying magnetic field, third by varying area of the coil, and fourth by varying angle. Okay. So in the next class we will study. Okay, we don't have to do with the changing number of terms because it is not easy to change continuously the number of terms and will produce and to produce an EMF. Okay, but remaining things are very easy. Is dB by dt. You can alteration. You can do alteration in your magnetic field also. You can vary your area also, and you can vary the angle also. Okay, our electricity is produced, yes, by this method. The EMF we getting in our home, that is produced by d by dt and cos theta. Okay, remaining all the themes are constant and we getting our EMF using this concept. Clear, beta? This is the rule for production of AC, alternating current, that we are using at our domestic supply. Clear? So in tomorrow classes, we will study the different type of electromotive force development. You can see here, there is a change in area. Like this is a complete coil. Yes or no? So check the coil is length from PQRS. The effective length of the coil is equals to PQRS. Okay. This is a movable length. And when you bring this length inside, like coil, this part of this limb PQ become here. Yes or no? Now tell me, the effective area become increases or decreases? Surely decreases, because previously the area is up to here, big one area. Yes or no? But when you this limb this when you keep this limb closer, then your area becomes this one. Okay, so your area decreases, right? Okay, so there is change of area takes place, dA by dt, right or wrong? And we will produce EMF. Clear? So we will see in which way you can produce area. Then there is a sorry, produce the EMF. Then in next one, we will rotate the coil and rotating the angle, and we will have the amount of EMF. Different cases we have the numerical. Okay. So in tomorrow class, we will see in which way we will produce EMF.